In this session, we're going to change the geometry to a cylindrical cavity, and we're looking to TE and TM mode inside this cylindrical resonator. Similar to the discussion for the rectangular resonator, we also set boundaries around z direction and set up standing wave around z direction. And so if we talk about TM modes, we start with the z component electric field. And the solutions was borrowed from the solution given by the cylindrical waveguide. But now we have the wave propagating around plus z direction and also minus z direction, setting up the standing wave around this z axis. And for this solution, we choose this sign to be plus, so that we get the cosine solution around z direction. That is because the z component of the electric field is perpendicular to this z surface. So you will be expecting maximum electric field, normal component electric field on the surface. Therefore, you choose this cosine solution. And to maximize the field on this surface and also on this surface, you specify the beta value to be equal to q pi over d. And once you specify this beta value to be q pi over d, then you can put it into this dispersion relationship to calculate the resonant frequency. And so think about that we have a solution of the z component electric field, which is proportional to this the Bessel function of the first kind of order n right here. But this the z component electric field is a tangential component of the electric field to this R boundary. In other words, if you set the R to be equal to A, which is the radius of this circle, then this the z component electric field has to go to 0. So this means that the HA has to be equal to the zeros of the this Jn function. And I have this plot for you to remember what we have before. And if we plot the Bessel function of the first kind of order 0 and order 1, you see this oscillatory curve around the x direction. And this point is the first zero of the Bessel function of the first kind of order 0, which is the 2.405. And this point is the second zero of the J0 function, given here is the 5.520 value. And for this point is the first zero of J1 function, which has a value of 3.832. And this point is the second zero of the J1 function. So if you specify the more number of n, then you can match the boundary condition to those 0 points by specifying this condition. So once you calculate this eigenvalue along the R direction, h equal to xmp divided by a, then you can calculate the resonant frequency. And this is the kz, the k value along z direction we just derived on the last page. So let's put this expression into this. Then you have the resonant frequency depending on A and D at the same time, the zeros of the Bessel function and also q pi. So the specific expression for the resonant frequency for Tm n pq mode is given by this expression. For example, if we choose q to be equal to 0 and choose the first 0 for the J0 function, then we will be able to calculate the resonant frequency of the Tm010 mode given by this expression by specifying this q to be equal to 0 and specifying this xmp equal to 2.405. So you end up having this a resonant frequency for Tm010 mole. So once you have the Z component of the electric field, you can also calculate all other field components inside this resonator. And I want to remind you that the first mole index refers to the variation along phi direction. And the third index refers to the field variation along Z direction. And this 1 or 2 or 3 is the 0 of the Bessel function. The first 0 of the GA0 function will give you 0, 1. And the first 0 of the GA1 function will give you 1, 1 in this mole indices. So let's keep the mole number to be 0, 1, 0. Then we can write down the Z component electric field to be like this. For this 1, for this 0, you put 0 for your Bessel function. For this 1, you pick up the first 0 of the Bessel function GA0. And then you have this expression for your Z component electric field. Then once you have this expression, you can calculate all other field components. For example, for this Tm010 mole, the only other field component is a phi component of the magnetic field, given by this expression. This H number is already decided by this X01 divided by A. So the H number inside this, the GA1, remains the same. But you see this GA in front of this phi component of the magnetic field compared with the Z component of the electric field. So there's a phase difference, 90-degree phase difference between this Z component electric field and the phi component of the magnetic field. And all other field components are equal to 0 for this Tm010 mole. So the mole field is particularly simple. You have Z component of the electric field, and then you have phi component of the magnetic field. So if you want to design a cavity for an application requiring a strong electric field along Z direction, then this is going to be the mole you want to excite. But it's interesting to see that the phase between the Z component electric field and magnetic field is different by 90 degrees. So if you calculate the Poynting vector, the average power flow along all direction, you multiply these two together and take real product of it. Those are phasor field. Turn out that it's equal to 0 because if you multiply this with this, you don't have any real value from this calculation. So this means that there's no average power propagating along the radius direction. And this is expected because along this R direction, you have a standing wave. And a standing wave does not carry average power in any direction. Also, we can calculate the quality factor for this Tm010 mole inside this cylindrical resonator. Well, first we just calculate the average stored power inside. So you want to figure out the electric energy density and also magnetic energy density and integrate them over the volume. But we knew that the electric energy, average electric energy is equal to the average magnetic energy inside. So you can just calculate one of them and multiply it with the factor 2 to get the final answer. So let's pick the field to be the Z component of the electric field, and then put the energy density inside this integrand, and then integrate over the volume. The differential volume is equal to d, which is the distance between these two end plates for the cylinder. And then you multiply with 2 pi r dr. It's going to give you a differential volume. And then you put the solution of Ez into this expression and do the integration over a radius from 0 to a. You are going to get the total average electromagnetic energy stored inside this volume. And for the power loss on the side wall, you want to first determine the surface current on this conducting wall. For example, the lines tells you the direction of the surface current induced by the phi component of the magnetic field. You have the phi component magnetic field denoted by those blue lines. So on the surface of this, the R equal to A, it induced the surface current along z direction. So there's still integration of the power loss density over the surface. Turn out that those currents are now function of z. So you can just multiply this loss density by the surface at R equal to A. But on this end cap, you also have the surface current induced by phi component of the magnetic field, given by those purple lines along R direction. So if you calculate those surface currents from the phi component of the magnetic field and integrate over the surface, but you have two surfaces, so you put the factor 2 in front of your calculation. Then adding these two components, you'll get the total power loss on this on the surfaces of this cylindrical resonator. So once you have the power loss, you have the stored energy inside, so you can calculate the quality factor Q given by this final solution. So this is the steps showing you to do the calculation for this quality factor. And we can also follow the same steps we just had for the Tm mole inside a cylindrical resonator to calculate the Te mode inside this cylindrical resonator. But now we want to focus on our attention to the z component of the magnetic field given by this expression. Again, you specify the wave propagating along z direction plus z direction and minus z direction, because once you put boundaries to this z equal to 0 and z equal to d, you expect standing wave set up along this z direction. And don't forget that this is the dispersion relationship provided by the waveguide analysis. And this z component of the magnetic field on this surface is going to be a normal component of the magnetic field on the surface, which is going to be equal to 0. So you choose the sign of this plus minus here to ensure that you have 0 normal component of the magnetic field at this boundary and at this boundary. So you choose the sign solution for this Hz component along z direction. Because if you set z equal to 0 or z equal to d, you don't have the normal component of the magnetic field on those conducting boundaries. And once you choose the beta value to be equal to q pi over d, you cannot set q equal to 0, because if you set q equal to 0, this z component magnetic field disappears. So q starts from 1 and then 2, 3, 4, but you cannot choose q to be equal to 0. So now we want to find out the value h from additional boundary conditions. Another boundary condition is that the tangential component of the magnetic electric field at R equal to A is equal to 0. So you can calculate the phi component of electric field from this z component of the magnetic field to have this expression, and set this R equal to A. The phi component of the electric field at this boundary has to be equal to 0, because it is a tangential component of the electric field on this R equal to A boundary. So this means that the J prime n of HA has to be equal to 0. So this means that this H is related to the 0 of the differentiation of the Bessel function. And I put this diagram here to remind you that we have discussed this before. For example, the first zero of the J1 prime function will have a value equal to 1.841 matched to this point, because at this peak point, if you do a differentiation, you get zero slope at this location. So once we know the eigenvalue h from the zeros of the differentiated Bessel function, then we can calculate the resonant frequencies. Well, previously we already know that this beta is equal to q pi over d, and q cannot be 0. And also we have this h value from these zeros of the differentiated Bessel function. So you can calculate this resonant frequency equal to this expression. And remember, q cannot be equal to 0. So you have the resonant frequencies for TE and PQ mode with q not equal to 0。所以呢，在这个小节里头我们把这个共振腔的几何形状从矩形变成圆柱状。那这整个分析它的物理呢，跟之前的这个矩形的共振腔非常的相似，只是在这个数学式子里头，我们必须把以前我们学的 Bessel function 再拿出来用。那所以呢 ，cylindrical resonant 基本上只是把它这个 cylindrical waveguide 的两端再把它放上这个边界，然后呢放上边界之后呢，在 z 的方向上头就有这个 standing wave 的这个产生。那这 standing wave 呢它的边界条件可以一连串的算出它的这个共振腔的特性出来。那我这里要特别强调就是 TE n PQ mole 或 TM n PQ mole 这里头的这几个 mole number 呢 ，n 是代表在 phi 这个角度方向的 variation， p 呢是指 r 的方向上头，你在取这个边界条件的时候呢，是取第几个 Bessel function 的零点。那这个 q 呢是 z 方向的这个 mole number。那所以呢，这个 p p0 很重要，这个 p 呢决定了这个 mole 的一些特性譬如说这个，如果是你在考量 Tm mole 的时候呢，那这个 p 是跟这个 j of n Bessel function of the first kind of order n 有关系，但是你在考量 T mole 的时候呢，这个p 还有它零点呢是跟这个Jn 这个 Bessel function 的微分有关系。那综合这个讨论之后，我们得到两个很有用的式子。这两个式子呢是计算这么一个圆柱状共振器里头它的共振频率。那这个左边这个式子呢是它的Tm mole 的resonant frequency。那右边这个式子呢是 Te mole 的 resonant frequency， 跟它的 mole number有关系，还有它几何形状有关系。但是对于 Te mole 来讲的话，这个 q 不能取0，所以这是这个小节里头的几个重点。谢谢。